Okay. Hello, everyone. Hello. Can everybody hear me? Sorry. Okay. So it is 5 o'clock now, so we will go ahead and get started. So this is the Physics 2054 final exam review. I hope that you're in the right place. Okay. So everybody ready? Hopefully we have enough seats for everyone. Okay. So we're going to start with number 1. It's saying which vector best represents the net force on Q1. So we'll go ahead and do this. So this is Q1. So to make it easier, we're just going to label the other charges so that we know what we're talking about. So I'm going to call this one A, this one B, and this one C. So if you guys remember, I know it's been a while. Are there any open seats next to anyone? Okay. Okay, we have a full house. All right. So we're going to look at the force due to each of these particles here. So this is a positive charge and this is a negative charge. So would they be attracted or repelled? Attracted, right? So the force on this one. So this right here is going to be the force due to A, due to charge A. So that's going to be that force right here. And then now we're going to look at the force due to charge B. So we're going to draw, it's also going to be attracted, right, because it's a positive and a negative. So we're going to draw a vector right here. So that's going to be the F due to B. So yeah, whenever you're given a question like this, just look at the force due to every particle around it. Sometimes it'll obviously be repelled. If this were positive, then it would be going the opposite way. Okay, and then we're going to look at the force due to this one. So it's also a positive and a negative, so it's going to be attracted. So that's going to be pulling that in towards that. So this is the F due to C. So to find the net force, we're going to need to add up these vectors right here. This one is kind of an easy one because, as you can see, these two here, they're opposing each other. So these are going to cancel out, so I'll just kind of cross that out. So you're only left with this here. So the answer for this one is just going to be B because that's the only force that's not going to be canceled out when you add up these vectors. Does everybody understand that one? Pretty good? Okay. So now we're going to go to number 2. I'll move it up a little bit. Okay, so it says, what direction would the force on an electron be in an electric field pointed downwards? So let's see if we remember what electric field is. I know it's been a long time. So if you have a positive particle, do you think that the electric field lines would be going out of the particle, out of the positive, or would it be pointing inwards? Does anyone remember? Out. Good. So it's going to be going out, positive. And then it's going to be in towards the negative. So these are the electric field lines, sorry. So if the electric field is pointed downwards, then that means that there could be either just one positive charge or a bunch of positive charges. I'm going to draw it like this. And the field lines are going to go down, out from positive into negative. So just always remember that the electric field goes from positive to negative. That's very important. So for an electron, so let's say there's an electron in this here. So we know that this electron is going to be attracted to the positive right here. Therefore, the force is going to be upwards on that electron. I know that seems kind of confusing because it's opposite of the electric field, but that's just an important thing to note about electrons. So this is going to be the force on the electron. And if that were a positive charge, it would be the opposite, right? The force would, because the positive charge wants to go down there. So that would be the force on the positive charge. So we can say that electrons' force goes against the field. Goes against the field. So for this question, it would be upwards, right? Because we said that it's going to want to go upwards towards those positive charges because that's how the electric field works. So it's going to be upwards. Good on that one? Okay. So number 3. So it says, which of the following is true of the figure below? There is some point between two charges where the electric field is 0. There is some point between the charges where the V, which V, that's the potential difference. Potential difference. So that's what V is, and then both A or B or neither A or B. So we said before that the electric field is going to travel from positive to negative. So it's going to be like that. And if you were to draw like the field lines here, it looks something like this, like up at the top like this. And then it's always going to go out from that positive still. So like kind of like that. And then eventually it's just going to be completely going like out, and then that's in. So that's kind of what the, so we're in towards the negative, out of the positive. So the question's asking if there would be a point where the electric field is 0. So if you have like, because these are our electric field lines right here, right? So since we have these electric field lines, it wouldn't be possible for it to be 0, right? Because we have those like those vectors. So like if there was nothing there, like for example, if you had 2 positive charges, all these want to do is go out, right? So it's like that kind of. I know this isn't the best drawing. But if you had 2 like charges, then like right in the middle, E would be 0, the electric field was 0. But when you have like different charges, it's not possible for the electric field to be 0 in between those charges. Okay, and then for the potential difference, if you guys remember what the potential difference is, it's kind of basically saying like around the positive charge, you have like a so I'll kind of like redraw this down here. Can you guys see it? Okay. So like around this positive charge, you have a positive potential difference, and then so like and they have like those equipotential lines, right, like that. So it'd be something like this. So positive. All these numbers would be positive, basically. And then around the negative, I know this is a horrible drawing, but these would be like negative numbers. So like you'd have like negative 100 volts or something, and then like 100 volts. So if you're going from like negative to positive, there has to be some point where it hits 0, right? Because like if you're going like negative to positive, 0's in the middle of that. So for like right around here, that'd be like where the V is 0. So the answer to this one would be B. And then kind of the same thing, if we had like 2 positive charges, I do those 2 close together, the equipotential lines would look something like this. And if you guys don't remember what equipotential lines are, it's basically like any point like on this line here would have the same potential difference. And any point on this line here would have the same potential difference. It's basically just, you can kind of think of the electric potential as like the potential for potential energy. That's kind of how I thought of it. I don't know if that confuses you more. But yeah, that's basically how that works. Any questions about this one? Good? Okay, so we will go to number 4. All right. I tried to keep some of the earlier stuff in the beginning. I know this one was kind of later on, but we will go with it. Okay, so the question says, where is the south magnetic pole of the current loop? So what we're going to do is we're going to use our right-hand rule. I know that's our favorite. Okay, so you're going to look at both sides, because you can kind of picture this as like a 3-dimensional loop. So like that's going out and then into the page like that. So it's like this, that, so out to in. So we're going to look at both sides and do the right-hand rule like on both sides of the loop. So let's start with this side. So it's going out here. So we're going to, and that's the current. And so our thumb's going to be the current. It's going to be out of the page like that. I'm trying my best to. Okay, so like out of the page. And then you see how it like curls like that. So like kind of like that. So it's going to be like this, right? Because you're going that way. And then on this side, it's going to be into the page. And then your fingers are going to curl the opposite way. Sorry if you can't see that, but it's like this direction, like this. So if you imagine this like a magnet, So first I'll just start like a typical magnet that you guys would see north to south. So for magnets, it's going to go like from north to south. So like out from north into south. It kind of makes you think of like electric field a little bit. Okay, and then so for this one, if you look at this, it's going out on the top and into the bottom, right? So like out the top into the bottom. So if we redraw this like a magnet, because we said before like it's going to go from north to south. So it's going to be like this, like out from the north into the south. I know there are more magnetic field lines that can be drawn in that picture, but we're just going to stick with like north to south. And that's north to south. So because of that, it's asking where's the south magnetic pole, so it's like this. So that'd be south, that'd be north. So the south would be on the bottom side, just because of the way that the field goes. Okay, so does everyone have any questions about this one? We're good on this one? Okay. Alrighty. So number 5, it says a dipole is moving in an electric field pointed upwards. So we'll label this electric field. When allowed to move freely, which direction will the dipole move? Okay, so we said before, if you guys remember, so if this is the electric field, what would the direction of the positive side be? Would it be in the same direction as the electric field or the opposite direction? Same, good. So it's going to be the same. And then we said before, so that's going to be the force. And then for the electron, it's going to be the opposite direction. So if you have it this side going up and this side going down, this is going to rotate like this way, right? So it's kind of go like that. So that would be the direction that it moves. So then that would be clockwise, right? Clockwise, everyone agree? So that's going to be clockwise. And just remember, the wording that I know Dr. Kong used in her lecture PowerPoints was that there's no net force, but there is a net torque. So if you ever get asked a question like that, just remember no net force, but there is a net torque. And torque is kind of like that rotational kind of motion there. Mm-hmm. Yes, yes, yes. Good question. Yeah, so the positive will always go in the direction as the same direction as the electric field. Okay, any more questions about this one? Good, all right. So number 6, it says in the figure, charge Q2, so this is Q2 right here, experiences no net electric force, so no net electric force. What is Q1? Okay, so first what we can do is we can draw the forces that Q2 will feel. So let's look at the force it's going to feel from Q1 first. So these are both positive. So if these are both positive, then there's going to be like a repulsive force, right? So Q1 is going to like want to push Q2 over this way. So this is going to be FQ1 on Q2. And that makes sense, right? Because like Q1, they don't want to be together, so it's like pushing Q2 away. But then this one's negative, so let's just call this one Q3 to make it easier. So then it's going to be a force in the opposite direction, right? Because they want to be together. So this is going to be force of Q3 on Q2. So if it says that Q2 experiences no electric force, then that would mean that these two forces would have to like be the same, right? They'd have to cancel each other out because they're going opposite directions, and that's the only way that there'd be no net electric force. So therefore, F of Q3 on Q2 equals F of Q1 on Q2. All right, so now we're going to start using some equations now because we're out of the conceptual stuff. I'll go ahead and write like the force equation up here. It's given, I have Dr. Kong's formula sheet that you guys will use in your final exam. If you guys haven't seen this yet, she did post it. So you are given this Coulomb's law, that's for force. You guys probably know that. So force equals K Q1, Q2 over R squared. So that's going to be our force equation. Okay, so for F of Q3 on Q2, I'm not going to put in values for the charges. Well, I guess we all know the value of Q3 anyway, but we're not going to worry about that at the moment. So we're going to do K, Q3, Q2. I forgot the other one. Okay, Q2. Okay, so let's think about what the radius between Q3 and Q2 would be. So that would be pretty easy because you see this is Q3, this is Q2, so it's going to be 10 centimeters. And 10 centimeters equals 0.1 meters. It's going to be 0. So always remember to convert centimeters to meters. So it's 1 meters. I'm sorry? 0.1? Yeah, 0.1, right? Okay, yeah. Thank you, though, yeah. I could always be wrong. This is 0.1. Yeah, if it were 1 centimeter, then it would be 0.01. But if it's 10 centimeters, it's just 0.1. Because like 10 over 100 is 0.1. Right, yeah. No problem. Okay, so it's going to be 0.1 on both these sides. So 0.1 meters squared. So that's going to be F of Q3 on Q2. And then we're going to write F Q1 on Q2 equals K. So Q1, Q2 over, so the R between Q1 and Q2, it's going to be, you're going to add these up because Q1 is way over here and Q2 is way over here. So you have to add these up. So it's going to be 0.2 meters. That makes sense. Okay. So now we're going to take these two equations and set them equal to each other over here. And stuff is going to end up canceling out. That's why I didn't like plug stuff in, yeah, except for the radius. So it's going to be, so I'm basically just going to rewrite these and equal them to each other. So K, Q3, Q2 over, I'll go ahead and put an arrow like, because this is, -4 nanocoulombs. We'll plug that in on the next one. We probably could have done it this time. Okay, so over 0.1 meters squared equals K Q1 Q2 over 0.2 meters squared. Okay, so now as you can see, we have a K on both sides, so we can cross out the K's. We also have a Q2 on both sides, so we can cross out both of the Q2s. And we're looking for Q1. We already know Q3, so we can basically just solve this for Q1 now. So I'll rewrite this again. It's going to be -4 nanocoulombs. That's what Q3 is. So I just plug that in over the 0.1 squared is going to be 0.01. So that's why that's 0.01. And then that's going to equal, so Q1 over 0, so 0.2 squared is 0.04. Okay, so now we want to isolate Q1. So we're going to multiply this times 0.04, both sides. So then you have, ignore this negative sign because remember it's absolute value. Sorry about that. So it's going to be positive because the absolute value of negative number is positive. My bad. Okay, so it's going to be the 4 nanocoulombs times 0.04 over the 0.01 that you already have like on the bottom here. So you can just like think of these as like together, kind of 0.01 equals Q1. And if you solve that, it's basically just end up being 4 because 0.04 divided by 0.01 is just 4. So it's going to be 4 nanocoulombs times 4. So it's going to be 16 nanocoulombs. And remember that this is 16 times 10 to the negative 9th coulombs. We also could have converted that in the beginning, but either way is fine. If she gives you the answer in nanocoulombs, then it works out the same. Okay, so any questions on this one? Yes. Like, good. All right. Are we good to move on to the next question now? Just about? Yeah, okay. All right. So this one's going to be an electric field question. Okay, so it says a negative 12 nanocoulomb charge is located at the origin. So we'll go ahead and like start drawing this. So if you draw like a kind of a graph. So this right here is going to be negative 12 nanocoulombs. Okay. So it says, what is the strength of the electric field at the position x, y? And then it says, so 0, 5 centimeters. So if you guys remember how to like graph things, it's probably been a while since you've done that actually. So it's going to be 0 and then up 5. So 1, 2, 3, 4, 5. So that's going to be, we'll call this point A, I guess, point A. Okay, and then we'll go ahead and draw the point for point B too. So it says, what is the strength of the electric field at the position negative 5, 5? So it's going to be negative 1, 2, 3, 4, 5, and then up 5. So it's going to be right about here. Okay. So that's going to be B. All right. So for A, so the formula for electric field, let's do that first. It's on your formula sheet. Once again, oops. So it's going to be KQ over R squared. So that's the formula for electric field. So don't get that confused with force. So that's electric field, and this is force. Okay. So I'll write that up here. Electric field equals KQ over R squared. Okay, so for this first one, we already said like it's up 5 centimeters here. We said basically this is 5 centimeters also. Well, that's not important for part A. So if it's 5 centimeters, then that's going to be our radius. So for this one, the R would be 0.05 meters, because we always have to convert our centimeters to meters. Okay, so the electric field is going to be KQ over R squared, so 9 times 10 to the 9th, that's what K is, and that's given to you. Q, we already said it says it's negative 12 nanocoulombs. For this one, it's not important, like the sign of the charge when it says, I know I probably should have said magnitude, but, so we're just going to say positive 12, so 12 times 10 to the negative 9th. When it gets important is when you're doing like voltage questions, like potential difference questions. I think I put one of those on here, so we can do that. So 12 times 10 to the negative 9th coulombs. That's what Q is. And then we already said what R is, so it's going to be over 0.05 meters squared. So that's the equation for this point right here. And then if you plug this into your calculator, you should get 4.3 times 10 to the 4th newtons per coulomb. And you guys can double check me on that, but it should be correct. Okay, so that's what that one is. So then for part B, R is a little bit more tricky for part B. So if I like redraw this, we have it going 5 centimeters this way, and then up 5. So then the point's like over here, right? Here, we'll just have. So that's what our R would be, because like this is the point, that's the 12 nanocoulombs. So we have to do the Pythagorean's theorem, right, to find what R is. So it's going to be, so basically 0.05 squared plus 0.05 squared equals R squared. And that's you're going to end up getting, I'm just going to leave it under the square root sign because we're going to have to square it anyway, because R is like squared in the equation, just to make it a little easier. So it's going to be the square root of 0.005. So that's what R equals, not R squared. So then we're going to plug this into our equation. So we write it KQ over R squared. And that's going to equal, so 9 times 10 to the 9th, as usual. The same Q, it's going to be 12 times 10 to the negative 9th coulombs. So So like I said before, if r is the square root of 0.005, then r squared just is 0.05. So that's what r squared is going to be equal to 0.005. And then for this one, I did not put in scientific notation, but it's 21,600 newtons per coulomb for this one. Okay. Any questions about this one? Good? All right. So now we're going to number 8. So it says, two identically closely spaced circular disks form a parallel plate capacitor. So I'll go ahead and start drawing this. So we have like 2 disks. I know these aren't very circular, but they're supposed to be circles. So transferring 1 times 10 to the 9th electrons from one disk to the other. So I'll just write 1.1 times 10 to the 9th electrons. Sorry if you can see it, but that's just electrons. From one disk to the other causes the electric field strength between them to be 2 times 10 to the 5th newtons per coulomb. So if these are parallel plate capacitors, one of them has to be like positive and the other one has to be negative. So I'll just make this one positive, because in this one the direction isn't important because they don't like really specify, but just for the sake of solving order like that. Okay, so then that would be the direction of the electric field, because positive, negative. Okay, so, and then E equals 2 times 10 to the 5th newtons per coulomb. And then we want to know what the diameter of the disks are. I shouldn't have put so much up there, so like what D is. Okay, so let's look at what we know here, because I know there's a lot of different equations, so you may not know immediately like which one to go for. So we're given the electric field right here, and we're given that these are parallel plate capacitors, so that means you're going to have to use one of the parallel plate capacitor equations. And we're given the amount of electrons. So pretty much whenever you're given electrons, you can kind of think to yourself that you're going to need to convert that into coulombs, like into charge, because there aren't many equations that like just use electrons. So we can go ahead and do that for a start. So we're going to call this capital Q, because remember for parallel plate capacitors, capital Q is basically like the absolute value of both of these. So like if this were 1 nanocoulomb and this were -1 nanocoulomb, Q would just be 1 nanocoulomb. So you kind of think of it like the absolute value of like either of them. I know that kind of confused me, because just basically leave whatever charge you have on both. I'm going to cross that out though, because that's going to mess you guys up. Okay, anyway, so to find the charge, we're going to take the amount of electrons, so 1.1 times 10 to the 9th electrons. And then we should be given the, okay, so and we're given that 1.6 times 10 to the negative 19th coulombs, and this is on your formula sheet also, coulombs per 1 electron, so that's going to cancel out electrons. And then we're just left with coulombs. So, and I got 1.76 times 10 to the negative 10th coulombs. And always be careful how you put this in your calculator. I did it wrong at first myself, so be careful. All right, so now we have what Q is and we have what E is. That's E. So now let's look at our equations. Let's see if we can find it. So electric field. So this is the electric field inside parallel plate capacitor. So we're given E, and we know Q. And this is a constant right here. I know it's hard to see, but that's like the epsilon naught constant, if you guys remember that. And then area. And so we know that we want to know what the diameter is, and area is pi r squared. So from this, we can find the diameter, right? Because like if you know the radius, if you multiply it by 2, you can get the diameter. So this is going to be the best equation to use for this one. So I'll go ahead and write that on here. And that's kind of how you can work through these problems. Like look at what you're given and think about how you can like manipulate it to get what you want. Because I know it can be difficult when there's so many different equations. So yeah, for this one, E, and E is electric field, equals Q. We know Q over E naught Okay, so the way that I would solve this, I would rearrange this and write it in term like A equals whatever this is. So I'll write it over here. So A, if you rearrange this, equals Q over E, which is electric field, times epsilon naught, which is the constant. So don't get those confused either. Okay. So, and we know that A equals pi r squared. So I'll rewrite it again. Pi r squared equals Q over E times epsilon naught. So now we can solve this for R. And then once we find R, we can multiply that by 2 to find the diameter, because we want to know the diameter. So to rearrange this for R, you'd basically just divide by pi and then take the square root, right? So then you'd end up with R equals the square root of Q over E times epsilon naught pi. Right? Everyone agree with that? Okay. So we're going to do the square root. We already know what Q is. That's what Q is. 1.76 times 10 to the negative 10th coulombs. And then we're given E, 2 times 10 to the 5th newtons per coulomb. Okay. And then epsilon naught is 8.85. And this is given. You don't have to memorize this. 8.85 times 10 to the negative 12th. And then pi is also on the bottom. So that's going to be times pi. Okay. So you can put all this into your calculator, and you should get that R equals 0.0056 meters. So that's what R should be. So to get D, because like you guys probably remember though, like because that will be R. So then this whole thing will be D. So R times R. Okay, R times 2, 2R. So we're going to do 2. So D equals 2 times 0.0056. And you should, and also whenever you do stuff like this, don't round. So in the calculator, it ends up being like 0.0056259. Because sometimes with rounding errors, you can have a little bit of a different answer. It's not a huge deal though. Okay, so and then it's going to be 0.011 meters for D. Okay, are there any questions about this one? Should be good. And just a side note, a quick side note, I didn't put anything about like electric potential energy, but just to remind you guys like kind of what that is. Let's say you have like a positive, like a positive charge moving towards this positive plate. What do you guys think? Do you think that its electric potential energy would be increasing if like you're moving it towards a positive plate, or would it be decreasing? Do you guys know? I think I heard a mixture. Increasing? It should be increasing, right? Because basically you can kind of think of electric potential energy. If you're like moving it where it doesn't want to go, then the electric potential energy would increase. So like this positive particle, it doesn't want to go up here because like there's a bunch of positive charges right here, right? So like as you're moving it closer to all those positive charges, the electric potential energy is going to increase because like when you let go of that positive charge, it's going to like go way down because it like wants to like get away from there. And it'd be the opposite, obviously, for an electron. If you move that towards here, that's where it wants to go. So the electric potential energy would be decreasing. Does that make sense to everyone? It should be a review. We're good? Okay. So let's move to number 9. So this is another parallel plate capacitor question. So it says a 3x3 parallel plate capacitor has a 1 millimeter spacing. So I'll go ahead and draw this. It always helps to draw things. Okay, I drew that weird though. Okay, so it's going to be 3 centimeters by 3 centimeters. And we'll go ahead and do the same thing we did before, like the positive plate by default on the top. It doesn't really matter though, and the negative on the bottom. And they're both 3x3. Okay. So it says they have a 1 millimeter spacing. So we're going to draw it like this. So that's 1 millimeter. And then it says the electric field strength inside the capacitor is 1.5 times 10 to the 5th volts per meter. And remember, volts per meter is also a valid unit for electric field as well as newtons per coulomb, so don't get confused if you see both of those. Okay, so, and I'll just draw the field arrow, so that's the electric field. So it's 1.5 times 10 to the 5th volts per meter. Okay, so the first thing, part A, it says what is the potential difference across the capacitor. So as we said before, potential difference is going to be just V, so don't get confused between potential difference and electric potential energy, because some people do, so that's just going to be V. So like, I'll just write that at the top again, potential difference equals V. So that's what potential difference is. Okay, so part A. So we're going to look at our equations again. And remember, this is a parallel plate capacitor. So let's find where the parallel plate capacitor equations are. So they're kind of down here. Let's see if she gave it to you. Okay, so we have V equals EX. And in this question, we're given the electric field as well as the distance between the plates. So you can use that as X. I know that's kind of confusing because usually you think of like D as that, but this will also work. I'm going to write it as V equals ED equals, so just remember the voltage is like the electric field times the distance between the plates for a parallel plate capacitor. Okay, so V equals ED. So so we're given the 1.5 times 10 to the 5th, so 1.5 times 10 to the 5th volts per meter, and then times the 1 millimeter. So 1 millimeter is going to be 1 times 10 to the negative third meters, right, because it's millimeters. 1 times 10 to the negative third meters. And if you notice, the meters end up canceling out, so that's how you know that you're doing it right. You can do this with pretty much any question, but so you're left with volts, and that's what we want. Okay, so when I did this, I got 1.5 times 10 squared volts, which is basically just 150 volts. I'm not sure why I wrote it like that, but that's what this one is. Okay, so then the other one, it says how much charge is on each plate. So for this one, this is given on your formula sheet. So charge, remember, that's Q. For parallel plate capacitors, it's the big capital Q, so that's a good hint, like that you're using the right equation. So I'll just go ahead and tell you guys this equation. It's going to be capital Q equals C, which is the capacitance, times delta V. So like that's the equation that we're going to start with. We're not given capacitance, so we can substitute another equation for this here, for capacitance. So capacitance is going to be, so C equals epsilon naught A over D, and this should be given in your, yeah, it is given. So epsilon naught A over D. So we can work with this, right, because we can calculate the area, and this is a constant, and then D, that's just the distance between the plates. So yeah, that's how we would do this one. So let's go ahead and solve for this one. So we're going to substitute this into this equation. So we're going to do Q equals E naught A over D times delta V. So yeah, if she gave you a question like this, she may just give you the capacitance instead, because I know it would be kind of difficult for you to like think through all this in a short time period. But yeah, if you weren't given the capacitance though, then you could substitute this equation in for that. Does that make sense, everyone? Kind of, okay. All right, so now we're gonna plug this in. So we know epsilon naught is gonna be the 8.85 times 10 to the negative 12. And epsilon naught does have its own units. I haven't been writing them because they're kind of long, but just keep that in mind. So 10 to the negative 12. So epsilon naught times the area. So for the area, 3 centimeters is going to be equal to 0.03 meters, and same thing for that one, equals 0.03 meters. So if you multiply 0.03 times 0.03, you'll get the area of this. And after you multiply that out, you'll get 0.0009 meters squared, and you guys can verify that. And over the distance, which is going to be the 1 millimeter, so 1 times 10 to the negative third meters. All right, and then times, and now that we found voltage before, we can find it, we can plug the voltage in for here. So that's going to be times the, basically the 150 volts. I'm not going to write it weird again. 150 volts. And that should be equal to 1.2 times 10 to the negative 9th coulombs. And remember, Coulomb is always charge. Okay. Any questions on this one? Should be good. Okay. So now we're going to move into more of the electric stuff. We weren't electric stuff before, but like circuits and like electromagnetic material. Okay. So let's do this one. Okay. So this one, it says, the wires shown below carry currents as noted, rate currents IA, IB, and IC. So if you guys remember questions like this, like the current in and the current out thing, so you probably remember like the sum of the current in equals the sum of the current out. Okay, so we're gonna look at like what's going in versus what is going out. So to me, it looks like IA is going like in, and then these two here are like branching out of IA. So like IA is going in, and then these two are like out that way. So I'm just going to write IA equals 3 plus IB, because like IA is going in, and then we have the 3A plus IB going out. Does that make sense to everyone? Okay. So now let's look at IB. So we're going to say IB and 2A to me look like they're kind of going in. So I'm going to write like IB plus 2. I'm just going to write 2 because writing 2A kind of can be confusing because that's just a unit. So I'm going to say IB plus 2 equals IC. So like these two are going in, and then IC is going out. So that's how you would go about doing this one. Okay, so now if we want to rank them, so we can kind of tell by looking at this that IB should be the smallest, right? Because like IB plus 2 equals IC, but IB plus 3 equals IA. So IB should be the smallest, just because like you have to add stuff to get IC or IA. And then IC will be in the middle because like I said before, like IB plus only 2 is IC, but then if you add 3 to IB, you get IA. So IA would be the biggest, and IC would be in the middle. Okay, so that's what I got, and that should be choice D. Yeah, choice D. Does that make sense to everyone? All right, so now let's move to number 11. Okay, so this one's a little more difficult, but we will get through this. Okay, so it says an electron travels with speed v between two parallel charge plates. So it's just a fancy way of saying like parallel plate capacitor. Okay, so I'm going to go ahead and like draw this. So this is the positive, and then this is the negative. And this is a similar question from the book. I think they give the picture. So the positive plates, the positives are on the top and the negatives are on the bottom, because that will be kind of important for this question. Okay, and then we know it's an electron. So the plates are separated by 2 centimeters, so I will label that. We could just call that D equals 2 centimeters. It says that they're charged by a 200-volt battery, so I'll just kind of write off to the side that like big V equals 200 volts. And then we're given that the velocity of the particle, and that's like little v, so little v, so I'll draw it like that, and then little v equals 2 times 10 to the 7th meters per second. Okay, so now it's saying what magnetic field strength and direction will allow the electron to pass between the plates without being deflected. Okay, so first, let's talk about the direction. So I'm gonna like redraw this like at the point where it'll be in between the plates, because like right now it's kind of like off to the side, but I'm gonna redraw it like this, just so we can understand it a little better. I'm gonna make it a little smaller. Okay. So this is the negative. Okay, so it says that it can't be deflected. So it says without being deflected. So that basically means that we want it to just like go all the way through here without feeling any forces on it. So therefore, because we know there's going to be forces on it, right? Because like there's going to be like electric force, and that's going to be up this way, right? Because like it wants to go towards that positive plate. So that's going to be the F electric, we'll call that. So we need to have some kind of force to put it down so that it'll like just be able to pass all the way through on here. Okay, so we have the velocity and we have the force. So doesn't this kind of make you think of the right-hand rule? Because if you have the velocity and the force, then you can use the right-hand rule to find the magnetic field, right? Okay. So if we are given that the force is up, so remember like the force is your like middle finger, and then the magnetic field is going to be your index finger, and then the velocity is going to be your thumb. So, and remember it's an electron, so it's kind of different for electrons also, but I'll go through that. Okay, so we have the velocity going this way. We know that the force has to be up, so I'll kind of do it like this. Like the force has to be up, sorry, I know it looks bad. So the force has to be up, and then the velocity is this way. So then if this were a proton, then, let me make sure. Yeah, so if this were a proton, then your magnetic field would be in, right? Because it would just be like this. But because it's an electron, it has to be out the opposite way. Because you want your force, wait, hang on. I think I explained this wrong. Okay, let's redo this. So we have the velocity going this way, right? We want the magnetic field to be going, the force to be going down. So the magnetic field force is going to be going down like this. You have your velocity like this. So if this were a proton, then the magnetic field would be going out. But because it's an electron, you basically kind of take the opposite of that, so it'll be going in, if that makes sense. Because remember, for an electron, like you can either say that the velocity is going the opposite way, or you can just basically take whatever, like the opposite. So yeah, does that make sense to everyone, kind of? I know it's a little confusing. Okay, I will try to explain this again. All right, so I know in class, Dr. Kong had said that you can kind of look at it for an electron that the current is going the opposite way, because remember that current is the movement of positive charges. So because this is an electron, you can kind of say, okay, the current's going the opposite way. So, and we know, and I'll go ahead and write this on here. So the magnetic, we want the magnetic force to be down because we want it to have equal and opposite forces. So the velocity is going to be going the opposite way, or like the current is going the opposite way. And then we have the magnetic force, which is going to be your middle finger going down. I'll do it on here so people can see it. So like your middle finger is going to be going like pointing down this way. So then your magnetic field is going to be going in, right? Because like, so the velocity is this way, your magnetic force is going to be going down, therefore your field is in. Does that make sense to everyone a little bit better now? I know it's kind of confusing to think about, because just use your right-hand rule, so like this. Yes, that's another thing you can do. So you can use your left hand. Basically, an electron is just like the opposite of a proton. So you can either like change the direction of the velocity, or you can change the direction of, I think the book says to just like take the opposite force. So you can say like, okay, the force would need to be like up on an electron, and your velocity is the same direction, so then your field would have to be going like in like that also. So you still get the same thing. So I'm gonna draw the in. I know this is confusing to think about, but so does everyone kind of understand it though? Yeah? I keep on getting it going, like with my right hand, I keep on getting it going into the in, right? It's supposed to be the opposite. Okay, 1 second. Okay, let's do this one more time. Okay, so I'll do it the way the book does it and say that the force is going in the opposite direction. So the velocity is going to be going this way, and then we want the magnetic force. Yeah, okay, sorry. We want the magnetic force to be going down if it were like a proton, but because it's an electron, we'll just like do the opposite way, right? So then it should be going in, right? Isn't that what I said? Yeah. Okay. Okay.
Yeah, according to right-hand rule, the magnetic field's going in, but because it's an electron, it would be opposite.
Opposite, right.
Magnetic field.
The magnetic field will be going.
Could you do it the way, like, the normal way, and then tell us the opposite, like you did the first one?
Okay, so the normal way tells opposite. Okay, so let's say that this were a proton. So then, my pen just broke. So if this were a proton, so the velocity would be going this way, right?
Yeah.
And then we want the magnetic field, or the magnetic force, to be going down like that. So for an electron, for a proton, it would be going out. So then for an electron, it should be the opposite going in, right?
Yeah.
I mean, you guys can tell me if I'm mistaken, because like, see, like, because you want the magnetic force to be going down, the velocity would be going this way, so then the magnetic field would be going out if this were a proton, but because it's an electron, it would be the opposite.
Okay, so for an electron, we want the force going up like this, and that way it would be going into the page, but we'd have to do it
Right.
out of page because it's an electron. Yeah, yeah.
Right, yeah, do you kind of get it? Okay.
Then like the arrows going down for a magnetic force, that's wrong on the picture? Is that still right?
That's still right, because like, so the force on this electron, the electric force is going up. I think you guys are confused because you see the electric force on top. We want the force to be down for magnetic, because we already know that.
Like not the induced, but like what we're trying to get so we can.
Right, yes, good, yeah, because like we want that downward force, so that's why it should be like into the page, because like that's the only way that would work. If you guys have a lot easier, yeah. You can use your left hand also. That's not the way I personally did it, but yeah, that also works. Okay, sorry about the confusion on that one. If you have any more questions, you can ask me at the end.
Can you just like kind of like say it one more time to like seal it into us?
Okay, I can do it with my left hand if you guys want. Okay, so the velocity is going to be going to the right that way, and we want the magnetic force to be going downwards like that, right? So the velocity is going this way. The magnetic force is going to be going down like this. I'll put it under here so people in YouTube can see it. So velocity down, magnetic field, magnetic force going downwards like that. So the magnetic field would have to be in with your left hand because it's an electron. Okay, sorry for the confusion on this one. I know this one's kind of confusing. She might not put this on there, but this wasn't one of your past exams if you have Dr. Kong. So yeah. I'm sorry? In, yeah. Okay, and then now we will solve this equation, or the actual values of this. Okay. So I said before that the magnetic force, has to be equal to the electric force. So like electric force is up, and the magnetic force is going to be down. F electric. So I'm kind of going to do this kind of quickly since we spent a lot of time. This part isn't as hard. Okay. So the magnetic force, this is an equation that's given to you on your formula sheet. So it's going to be Q VB, and that's the little v, so, and that's velocity, equals Q delta, that's like the voltage as big V, over D. So, and we have all these values. We can go ahead and cancel out Q on both sides. So we're left with just VB equals delta voltage over D. So if you like resolve this, because we want to know what the magnetic field strength is. So B equals voltage, that's that, over the distance times the velocity. And that's, once again, that's little v, this is big V. So we know that the voltage is 200 volts. And then the distance between the plates is 2 centimeters, which is 0.02 meters. Okay, and then the velocity was given. That's 2 times 10 to the 7th meters per second. And that's, if you plug this into your calculator, you should get 0.0005 Teslas And then we said that it should be in. Okay, yeah, sorry for the confusion on this one. Like some people said, just use your left hand. If that's probably the easiest way for the electron. And like I said, if you have any questions, you can ask me at the end. Okay, so let's move on to number 12. Okay, so number 12, it says the magnetic field at point P is 0. What is the magnitude and direction of the current in the lower wire? Okay, so let's do the direction first. So we have the wire on top. It's going this way, right? Like that's the direction of the thumb of the current, and that's your thumb. So then you know that your magnetic field, it's going to be going like kind of wrapping behind it like that. So it's going to be going from out to in, if that makes sense. So I'm going to draw that out to in. And like this wire here is going to feel that inward magnetic field. So I'm going to draw it like all the way down here. Okay, so even like point P, like it's going to be feeling that. Okay. And I'll make a key because I can, so I'll say like black equals, and we'll label this one on top wire 1, and this one on the bottom is wire 2. So the black equals the magnetic field B of wire 1. Okay, so we know that the magnetic field at point P is 0. Therefore, the magnetic field due to wire 2 would have to be the opposite of this inward force, right? Inward field, right? Because in order for it to be 0, like there has to be like opposing fields. So basically what we need to do is we need to figure out what current and what direction of current in this wire will make it go the opposite direction, like underneath it. So you can kind of like process of elimination. If you had it going the same way, then it would also be going in. So like it would just add more to that inward force, or inward field, sorry. But if it goes this way, then it'll be going, so assuming it's going this way, and red equals magnetic field of wire 2. So if the current is going this way, then we have it going like in on top like that, but then out here. So in order for like it to be possible for there to be 0 magnetic field here, it would have to be going that direction because like it has to go the opposite direction from what this wire would be. So that's the direction of the wire, and then now we need to find the magnitude of it. So we know in order for it to be 0, the magnetic field due to wire 1 has to be equal to the magnetic field due to wire 2. So I'm going to write B1. I'll move this up a little bit. Okay. B1 equals B2. And these equations are given to you, like I said before. So this is going to be mu naught times I1. So like this is I1 up here, and we'll say this is I2. Okay. I1 over, and then the actual equation itself, hang on, let me see if I can. Mu naught, let's see, does she even have it on here? There are a lot of equations. Yeah, okay, so it's going to be mu naught I times 2 pi r. So like this is the general equation right here. I'll get rid of the I1. Okay, so like that's the general equation. So then for B1, okay. So for B1, it's going to be mu naught I1 over 2 pi. Okay, and then we need to figure out what r would be for I1. So if we look on here, the distance between point P and I1 would be 6 centimeters plus 6 centimeters. So that's going to be 0.2 meters, or 0.12 meters, sorry, 12 meters. Okay, and then that's going to equal B2, which would be mu naught I2. Can you guys see that? Okay, mu naught I2 over, same thing, 2 pi But then in this case, this point P is even closer to wire 2, right? So that's going to be 6 centimeters instead of the 12 centimeters. So that's going to be 0.06 meters. Okay. And once again, we have stuff canceling out. So like the mu naughts on both sides cancel out. And then the 2 pi's cancel out. Sorry, I'll move that. Okay. And the 2 pi's also cancel out. So I'll write it over here. So you're left with I1 over 0.12 meters equals I2 over 0.06 meters. And then if you solve this, basically you just like multiply this times 0.06. 0.06. So 0.06 over 0.12 I1 equals I2. And that's basically the same thing as saying 1/2 I1 equals I2. And if I1 is 10 amps and 1/2 I1 is I2, then I2 would have to be 5 amps left, because we said that. Okay. Any questions on this one? Should be on this one? Okay. So now let's go to number 13. Okay. So this is similar to the torque question that we had before, except this one we're talking about magnetic field on this one. Okay. So it says if released from rest, the current loop will what? So we're going to use our right-hand rule again. Hopefully this time it'll go a little better. So we have our, so this is like a current loop once again, so it's going like from out to in. So whenever you're given a question like this, look at like both sides. Same thing as how it was for the electric one, because I know people get confused with this question sometimes. So let's start with this side. So your current is going out, so like your thumb's going to be going out, and then your magnetic field, which is your pointer finger, that's going to be going this way to the right. So then the force on this side would have to be going up, because that's like your middle finger like that. I don't know what that is. So yeah, like that's your middle finger going up like that. I know it's hard to see, but so it's like this. And that would be your force upward. So this side, the force would be up. We pretty much know if that one's up, the other one's going to be down, but we'll do it again just to practice. So the current is going to be going like in on that side, so your thumb is going to be going in like that. And then your magnetic field is going to be going to the right. I know it's hard to see under here. And then, so your force is going to be going down like that. So like this. And then it's like the same thing as how it was for the dipole in the electric field. So it's going to be kind of like that. So that should be rotating counterclockwise. Kind of understand this one a little bit?
That's clockwise.
You said counterclockwise, but you meant clockwise.
Oh, I circled clockwise, but I said counterclockwise, did I?
But did you mean clockwise?
I mean clockwise, yeah. Yeah, because it is clockwise. Sorry if I say counterclockwise, yeah. It is clockwise, because it's like going like this. Okay, sorry about that. Does everyone understand it now? Okay. So for number 14, it's another one of these electrons. So I will use my left hand, because that seems to be like the easiest way to explain this, besides like doing like the weird stuff. Okay, so it says the arrows represent the magnetic field. What direction would the force on the electron be in this field? So we should get this one right. This is the velocity moving down. Left hand. Okay, so your velocity is going to be going down. So like that's going to be your thumb like this. And then your magnetic field is going like this. So then using your left hand, it's an electron. The force should be into the page, right? Because it's like, it's like this. Like your magnetic field is this way, your velocity is going down like that. So then the middle finger, you can't see it on here, but it's like going into the page. So the force is in. You guys get?
If you do it the right hand, doesn't it go into it and be the opposite?
No, I'm doing the opposite.
So it'd be
Okay, so.
So if you do it the right hand,
Uh-huh.
and
Okay, so let's do it with the right hand just to see. Okay. So with the right hand,
oh yeah,
it's like this, so then it will be going like out like that, but it's actually like opposite of that force. Because like for the right hand rule, you have to take the opposite if it's for an electron. Oh, okay, yeah. All right. Does everyone kind of get it now? Wait. Okay, all right. If you guys have more questions, you can ask me afterwards. Okay, so let's go ahead and go to number 15 since. Okay. All right, guys. Okay. So number 15. So it says, suppose the switch in the below circuit is open when it, and we're out from the magnetic field stuff, I think, till the end, actually. Well, I think there's like one more. Okay, so anyway, so suppose the switch in the below circuit is open. When it closes, the battery current will do what? Okay, so this is a while ago. So right now it's open. Once it closes, keep in mind this is a parallel circuit. What will happen to the resistance when it closes? Like, do you guys think that it'll increase or will it decrease, like when the switch closes? Decrease, good, yeah, because it's in parallel, right? So like the more and more resistors you add, the lesser the resistance gets. So I'll just write when you close the circuit, R decreases, yeah, decreases. Okay, so now we're going to use good old Ohm's law, V equals IR. So we're going to look at this. So our voltage is just going to stay constant, right? Because like it's the battery. I guess you could also call that EMF because like usually for battery they say EMF. It's kind of the same thing. So we're going to say this stays constant. So the resistance we know is going down, right? So this goes down. So in order for the voltage to stay constant, the current has to go up. So for this one, when you shut that, like when you shut this switch here, the current coming out of the battery is going to have to go up. And that kind of makes sense because like the more and more resistors you add in parallel, like the more and more current you're going to have to pull out of here. Because remember in parallel, like each branch gets the same amount of voltage. So like if this were like 10 volts, then this will get 10 volts, and this will get 10 volts. And like if you added more and more, each one will get 10 volts. So like it kind of makes sense that like you have to pull out more and more current out of the battery each time that you add more branches. Okay, so does everyone have any questions? Yes? Good question. Okay, so if it were in series, let's say I'll just draw it like that. Like, so basically in series, you can't really have like a switch in series because like if you did, then you would like kind of break the circuit. But as you keep adding more and more resistors, the resistance increases. So that's a good difference between parallel and series, because in parallel, the more resistors you add, the resistance goes down. But in series, like if this were like 5 ohms, and this were 5 ohms, and this were 5 ohms, you would just add those in series. So like the more and more you add, so it's the opposite in series. Like if you added more resistors, then you'd have less and less current coming out because the resistance is going up. So yeah, it has to be the opposite. Good question though. Okay, so we're gonna go to number 16. So it's another circuit question. So it says a 12 ohm resistor, a 6 ohm resistor, and a 4 ohm resistor are all wired in parallel and are connected to a 12 volt battery. So first is to draw the circuit. We'll just quickly draw that. So we have a battery. It's 12 volts. And then, so that's one. You can kind of draw it like this and like kind of branch it off like that. That's another resistor. It doesn't matter like the order that you draw them in. Okay, so this one's 12 ohms. This one's, because that's what it says, 6 ohms. And then this one's 4 ohms. So that's our parallel circuit. So it says to find the equivalent resistance. So for parallel, as we said before, like it's going to, as you add more and more, it's going to go down. But the actual equation, the R equivalent, we call it that, it's going to be 1 over R1 plus 1 over R2 plus 1 over like R3. And then you just kind of keep going and adding that, and then to the -1. And to the -1, that just means like kind of inverse it. Like if it's a fraction, you just flip it, or you can plug it in your calculator like that. Anyway, so for this one, it's going to be 1/12 plus 1/6 plus 1/4 to the -1. For this one, I'm just going to turn them into like fractions, you know, like change the denominator on the bottom, because that's how I like to do it. So it's going to be 1/12 plus 2/12 plus 3/12 to the -1. So that'll end up being 6/12 to the -1. And then if you just flip that, because that's all to the -1 means. It just means like you flip it. So 12 divided by 6 would be 2. So your equivalent resistance would be 2. And notice how that's less than any of the resistors on here. Okay, so it says to find the current through the battery. So now we're going to use Ohm's law. So V equals IR, except for this one we're going to do I equals V over R. So we know our voltage. It's, move this up a little more. Okay, our voltage is 12. And then our REQ, like, so to find the current through the battery here, all you do is just take the voltage divided by the equivalent resistance. So it's going to be 2 ohms. So 6 amps. So that's going to be the current through the battery. Okay. And then part D, it says to find the current through each branch of the circuit. So as I said before, like each branch is going to get 12 volts because that's just how like parallel works. They each get the same amount of voltage. So like this gets 12 volts, this one gets 12 volts, and so does this one. Okay, so we're going to use the V equals IR for each equation. Well, I guess it'll be I equals V over R. So we'll call this like branch 1, branch 2, branch 3. So for branch 1, we have I equals V over R. It's getting 12 volts, and there's only 12 ohm resistor on here. That would be 1 amp. And then for the second one, we have I equals V over R again. So it would be 12, I forgot to put volts on top, volts. So 12 volts divided by 6 ohms, that'll be 2 amps. And then 3, I equals V over R again, so 12 volts once again, and then divided by 4 ohms, and that should be equal to 3 amps. Okay, so, and if you notice, these all add up to 6 amps, so that's how you know that you did it right. And if you also get a question like saying, like, if they give you the current out of the battery, you can pretty easily find each of the currents down here. What else? Yeah. Any more questions about this one? Okay. So if we are good, we'll move to number 17. Okay. So this is a capacitor in a circuit question. I know if you have like Professor Kong, she doesn't really go over this too much, but just in case, I figured I'd throw it on here. Okay. And I'll explain what I mean by the switch is shut. Okay, so it says like suppose the switch is shut. What is the current immediately after the switch is shut? So by shut, I mean like, so at this instance, you can like kind of ignore the 5 ohms. Like this 12 volt battery is charging up this capacitor right here. And when you do that, the capacitor ends up charging up to 12 volts. So like this will end up being a 12 volt capacitor. And there's a pretty easy way you can figure out like the charge on the capacitor too, like Q equals C delta V, I think. And they gave you the capacitance, but that's kind of just a side note. But if you were to find the charge, Q equals C delta V should give you the charge on that capacitor. Okay, so by shut, I mean like this switch is going to move over to this side, basically to make like this a new kind of circuit. So like because you have the 8 microfarad 12 volt capacitor, and then the 5 ohm resistor. Because I know it's kind of confusing wording, but that's basically all I'm saying. Like you're getting away from that battery and you're just like moving to the other side. So since there's like no battery to like keep the voltage in that capacitor, because like a capacitor can only hold like it like discharges the charge and like the voltage goes down also. But at the instant that you shut that, it's still just going to be 12 volts. So this one is pretty easy to find because like at the first instant that you shut it, it's just going to be the I0 because like that's just the initial like current that you have in that this little circuit right here. So like it almost is just like a battery at that point. So it's going to be the delta V capacitor over R. So it's going to be 12 divided by 5 ohms. Volts 5 by 12 ohms equals 2.4 amps. Okay, so that's all you would do for this one. I don't think she gives you the equations for this either, but if you have like other professors too, like you may see this on your exam. Okay, so for B, so as I said before, like as time goes on, you're going to discharge, you're going to get rid of those charges because like you have nothing to like keep the charge on that capacitor up here. So there is an equation to find that. It's going to be I equals I initial times E, and I don't mean to do this to scare you, because I know you guys probably haven't seen this equation in a while. Negative T over RC. So for this one, the initial current should be 2.4 times E to the negative 20 times 10 to the, why did I put 20? It should be 10. Negative 10, sorry, times 10 to the negative 3 over, so the resistance is 5, and then the capacitance should be 8 times 10 to the negative 3 farads. Okay, so my answer will probably not be right that I put on here, so if someone wants to like put this in their calculator really quickly so we can have the right answer, because I, for some reason, put 20 before someone, or I could just do it. So 2.4 times E to the negative 10 times 10 to the negative third over 5 times 10 to the negative 3. Okay, so that's what my calculator pulled out, so 1.87, if I did it right. Amps. Okay, so if you were to get a question like this, that's just how you would do this one. Okay, so now for number 18. So it says a 60 watt light bulb has a resistance of 240 ohms. At the operating temperature of a tungsten filament, the resistivity is approximately 5 times 10 to the negative 7th ohms dot meter. If the wire used to make the filament is this long in diameter, how long must the filament be? So whenever you're given resistivity, you can think of that equation, the R equals rho, that because like this weird P thing, that's rho L over A. Because like this is resistivity, and that's like the only equation that you can find that in. So it's a good guess that that's the right equation. Okay, so we want to know how long the filament must be. So we know the diameter of it. Based on the diameter, we can pretty easily find the area. So let's do, because like the cross-sectional area equals pi r squared, which is the same thing as pi times 1/2 d squared. So you can do it like this too. Okay, so if you go down and solve this for L, move that up. Okay, so you get L equals AR over P, right? Oh, rho, sorry, it's not P, it's rho. So for this one, the area is just going to be pi r squared, so it's just going to be pi times, I wrote in here 1/2 times 0.050 times 10 to the negative third meters, or you could just write that as 0.025 to make it not look like that. So it's pi r squared, right? So we're going to have to square that, and then we're going to multiply it times r, and we're given r, so that's 240 ohms. And we're given rho, which is 5 times 10 to the negative 7th ohms dot meters. So for this one, I got 0.94 meters. Okay, yeah, so for this one, basically just plugging into the formula, knowing which formula to use is the easiest thing. But if you're given rho, which is the resistivity, then this equation should be the one you use.
Does pi 1 have p on the formula sheet?
I'm sorry?
Does the pi 1 have p on the formula sheet too?
I doubt it. I don't think so. I think you're just expected. I don't think that the area formula is on there.
Oh.
So just remember, like, pi r squared is area, and then 2 times r is d, like the diameter. So that's just something that you have to remember. Okay, so let's go to number 19. Okay, so this is one of the power dissipated questions. So it says a resistor is connected to a 3-volt battery. The power dissipated in the resistor is 2 watts. The battery is then traded for a 6-volt battery, and then it's asking what the power dissipated is now. I'll go ahead and write all the power equations. You're given P equals IV on your formula sheet if you have Dr. Kong, but as you probably know by now, there's also I squared V, so I squared R, sorry. And you find this by manipulating Ohm's law and like plugging in stuff. So that's I squared R, and then V squared over R, that's the other equation. So whenever you're given this type of question, you want to find the resistor value, because if you find the current value, that's going to change when you change the voltage, if that makes sense. So like if you use one of the ones that have I in it, you could get the wrong answer just because like it changes and you don't want too many things changing. So a safe bet, we're given the V, the voltage, and we're given the power. So if we want to know R, the best thing to use would be this one right here. So if P equals V squared over R, then R equals V squared over P. So just have to manipulate that. So we're given that the voltage is 3 volts. So 3 squared would be 9. I'll just write it as 3 squared though. Over 2 watts. So then that's just 9 divided by 2, which would be 4.5 ohms. So that's the value of the resistor, and that's not going to change. So like once you have that resistor value, you can plug that in even if like the voltage changes. So now it's saying that the battery is traded for a 6-volt battery. So now we want to know the power now. So we want to know power. We know the voltage and the resistance. So we'll use that same equation. So V squared over R, which is going to be 6 squared over, that looks like a weird R, okay, over 4.5. And you should get 8 watts. So 8 watts is now the power dissipated by the resistor. So that's how you do a question like that. So remember, always start with finding the resistance for these types of questions. Okay. So for number 20, we're getting into like induced stuff now. This is like kind of getting towards the end of the course. So it says a metal bar moves through a magnetic field. On what side of the bar are the induced positive charges? So we get to use the right-hand rule again. Yay. Okay. So the velocity is going to be going like down like this. So like this, like that way. And then you know that the magnetic field is going outwards. One second. So the velocity is going outwards, downwards, sorry, and the magnetic field is going outwards. I know it's very hard to maneuver your hand like this. So it's down and the magnetic field is out. So then the magnetic force will be going this way. And remember, the magnetic force is always the direction of like the positive charges. So, or you can think of it as like negative to positive, like this side negative to positive. So the positive charges, if it's going this way, will be here. And then the negative charges will be here. Because like the force is going from like positive to negative. Yeah, I can't even do under there. So yeah, so right-hand rule. Hand rule. So it's asking where are the induced positive charges. So it'll be on the left side, right? Left side. Does that make sense to everyone, kind of how that works? Just remember the force is like where the positive charges are going. Okay. So for number 21, this is one of the single slit equations, or diffraction equations. Okay. So it says a laboratory experiment produces a single slit diffraction pattern made on a screen. If the slit is made wider, the bright fringes will be what? Okay, so I know this is pretty fresh in your mind, but I'll just draw the diagram again. So this is A, like it's the single slit, and then you have the wavelength going in like that, so like that's going into A, and then that's the length, and then I know I had this wrong before, but I have this right now. So this is like your central maximum, kind of like right here, but I didn't draw it very well, but like that's supposed to be kind of bigger, and then the YP, that's the length of the dark space, not the bright space, the dark space. So YP equals length of dark space. Yeah, and if you get confused, I would look at the pictures in your book because it's kind of hard to draw without like colors and stuff. So length of dark space. Okay, so I think the only like equation that she gives you for single slit is the one that you need to use for this one. But it's going to be YP equals P lambda L over A. And P is just kind of like the number, like dark space you're on, but that's not really important for this one. So it says so the slit is made wider, so if A is getting bigger, then YP would be getting smaller, because A is on the denominator, so like the denominator is getting bigger. Well, YP will be getting smaller. So if the distance between the bright fringes are getting smaller, then they're going to be closer together, right? Because like that, like the dark space is like decreasing, so they're like closer together. Does that make sense, everyone? I know I had this confused before, but okay. So number 22. This is, okay. So a digital cell phone emits 0.6 watts of 1.9 gigahertz radio waves. What are the amplitudes of the electric and magnetic fields at a distance of 5 centimeters? So this is like very similar question that we've done before. But so basically, whenever you're given questions that talk about like the electric and magnetic fields, finding both of them, immediately think of the intensity equations. Yes, yes.
Sorry, can we go back to 21 for a second?
Yeah, sure. What was the question?
You said YP is the length of the dark space, right?
Yeah, it's like the distance between the bright spaces.
It's the distance between the bright spaces.
Mm-hmm.
So if that's the distance of the bright spaces, and you said that A is increasing,
Mm-hmm.
oh, YP is also increasing. I don't know why I flipped in. Thank you. Never mind. Wait.
Oh, yeah.
Wait. Okay, wait. So
Uh-huh.
if A is increasing, shouldn't YP also, shouldn't it be decreasing? So
It is.
wouldn't the space be farther apart?
So YP is the distance between like, so let's say like these are two like bright fringes.
Because you know how like A is in the denominator?
Right.
The bigger the A
Mhm.
is, the smaller
The
YP
YP.
would be.
Right, you are right. So YP is getting smaller, but YP is the distance between like the bright fringes. It's hard for me to draw this. Like let's say, I do have colors. I always forget I have colors. Okay, so like, because in the drawings it has like the dark space and then the bright spaces. So like the red, that's where it's bright. So then this is YP right here. Okay, you guys can see that YP. So if YP is getting smaller. So you have like super tiny little black spaces now. This isn't like greatly drawn. But then the bright spots will be like closer together, if that makes sense. Because like see like these are farther apart because it has more black space in between. And because, and I'll draw this up here. I'll keep drawing that. This is not drawn to scale. I know I didn't do the best job at drawing this, but if YP is getting smaller, then see how these are like closer together than these because YP is smaller. There's less space in between them, if that makes sense. Yeah, I also had that confused myself. So make sure that you know YP is like the dark space.
It's basically the distance between the bright spaces.
Yes, it's a distance between the bright spaces. Yeah. Sorry for the confusion.
Thank you.
You're welcome. Okay. So number 22. I already read it, so I won't read it again. So I already said that the intensity. whenever you're being asked about the electric and magnetic fields, always think of the intensity equations. So she gives you like 3 of them. P source is one of them, over 4 pi r squared. So for this one, we're going to just use this equation because the other intensity ones, you already have to know the electric and magnetic fields for those ones, but this one, we have enough to use this equation, basically. So it says that the power, so like this is P source right here, that's P, and then this is R. So the power is going to be 0.60 watts, and it's going to be over 4 pi and then 5 squared. So, and then I got 19.099 watts per meter squared. Okay, so there's other intensity equations, and let me see if I can find it on here.
Do you have to convert that pi to meters on the bottom?
I think, yes, thank you very much. I did it in my work, but I did not do it here. Hang on one sec. Where was it? Yes, I did do it in my work, sorry. 0.05 meters. Good catch. Okay, so yes, it's going to be over the 0.05 meters squared because you have to convert that into meters. I was just looking to see, yeah, so she gives you these 3 equations right here. So we already used this one. Notice how, like, on both of these equations here, everything is a constant except for the magnetic field and the electric field. So once you have like intensity, it's pretty easy to find either the magnetic field or the electric field. And then there's the other equation that puts them together. I can't find it on here right now, but it's on here somewhere. It should be C equals E over B. That's the other equation. Okay. So we're going to go ahead and find E first. So I already showed you guys the equations. So it's I equals 1/2 C epsilon naught, and then this is electric field. I know it's confusing because they're right next to each other. So that's that equation. If you isolate this, because we want to know this, you get the electric field equals the square root of 2I over C E naught. So yeah, if you just rearrange that, then you get that. We're just going to plug everything in. So 2 times 19.099 watts per meter squared. And C, that's a constant. That's the speed of light. So that's 3 times 10 to the 8th meters per second. And then epsilon naught, we've used many times now, 8.85 times 10 to the negative 12. I put the units this time. I'll just write it in Newton dot meter squared. Okay, so that's what you will plug in for this one. And then I got 3.998 times 10 to the negative 7 Tesla. Okay, so we have epsilon naught, not epsilon naught, electric field. That's this E, epsilon naught's other E. Okay, so now we want to find what B is, right? So we can use this equation to find B because this is a constant, and then we just found what E is. So I don't have much space left. B equals E over C. Hang on one second. I'm very sorry. This, that is what you will get for B, but for this one you should get 119.9. It's the same values, but I accidentally wrote down what I got for B instead. But this will end up what you get for B. 119.95 newtons per Coulomb. So that's what E electric field is. And then once you plug in this, so 119.95 over 3 times 10 to the 8th, I shouldn't have crossed that out, then you get this. I'll just rewrite it. So B equals 3.998 times 10 to the negative 7 Tesla. Very sorry about that. Okay. So that's what E equals, and that's what B equals. Does anyone have questions about this one? And you could find B first if you wanted to also. I find the B equation to be kind of uglier than the electric field one, so I tend to start with the electric field. So let's go to number 23. So this should be fresh in your minds, hopefully, because this was like last week, I think. So it says, based on the figure, what is the direction of the current in the loop? So we're going to draw the magnetic field, and like the velocity is moving down. The magnetic field also happens to be in that same direction down here. Like that's the, and then it's, remember it's always into the south, out of the north. So that's into the south. Okay, so we're moving this magnet away from the loop, right? So the, we'll call this like inward, because that's like kind of into the loop. So so the magnetic field is decreasing inward, decreasing like into the loop. Okay, so if you guys remember, whenever it's decreasing, the induced field is going to be in that same direction, right? Because it wants to like oppose, like, because there's less and less, and the loop is like, no, I need like more and more to go in. So the induced field will be in that same direction. Will also be into the loop. Okay, so we have the magnetic field. It's like going like into the loop, like it's hard to picture this. Okay, so like if the loop is here, it's going like into the loop like that. So the the current should be in this direction, right? It would be like this, which should be clockwise, I believe. Clockwise current. So. Mm-hmm. Does anyone like? Mm-hmm. So I'll explain that. So the induced current, let's say like, whenever it says like, oh, it's increasing inwards, then the induced current, the induced field will be the opposite of that. But whenever it's decreasing, like, so like right now, this is decreasing inwards, the induced field has to be going in that same direction, because since you have like less and less going in, it wouldn't make sense to like put it in the opposite direction, because you already have less and less going in. So like, why would you help it out and like put it opposite of that lesser direction? I know it's confusing to think about, but just remember, if it's decreasing like if it's decreasing in the loop, so like if it said like when you guys had this drawing and it said decreasing inwards, the induced field has to be in that same direction, if you guys remember. And you can, yes.
Also, like, we put this on the last review and everyone got confused because all the examples in the PowerPoint flip it, where the north is on the top and south is on the bottom. But you have to keep in mind that since the south is on top,
Right.
it's like kind of flipped around.
Right, and she could do that in theory on the exam. So if it were the north on top, it would basically just be the opposite, because if you, I think in like a lot of her examples, she has it moving towards the loop, which is kind of
Lenz's law, it'll
good.
counteract.
Yeah, Lenz's law, yeah.
Because south is on top and north is on bottom.
Yeah, this is definitely like a trickier one than the ones that she has in hers. Yeah, because you probably thought of it as like it's always going to be opposing. But your question, if the north were up here and if you were moving it down, then it would be the opposite. Like you'd have like less and less force going like out of the loop, I guess you'd call it, like kind of like upwards out of the loop that way. Therefore, the induced would be in that same direction that way. And then based on that, you find the current. Sorry if that confused anyone, but she could ask it like this. So I just want to do like a more difficult type one. Okay, so if we're good on that, we will go to number 24 now. So it says a hot wire dissipates 600 watts when plugged into a 120 volt outlet. I don't have so much time left. Okay, so it says, what is the wire's resistance? So it's going to be, so we know that this is the VRMS. So to find the wire's resistance, P equals B squared over R. We're just going to use this equation. I know I'm going kind of fast, but we're running out of time. So if we rearrange that, and that's going to be RMS. R equals VRMS squared over P, and that's going to be 120 volts squared over 600 watts We'll ignore that. That should be 24 ohms. Okay, so that's kind of just like a plug and chug type of thing. Okay, so now it says, what are the RMS and peak currents through the wire? So we have power, and we have R, and we have VRMS. Well, yeah. So then now we can find the IRMS. So we have P equals IRMS squared times R. So IRMS, and that's just the root mean squared current, right? And I know I didn't say it, but keep in mind, whenever you're given stuff like this is going to be the VRMS, not the peak voltage. So the IRMS is going to be the square root, if you rearrange this, of power over R. So that's going to be square root of 600 watts over 24 ohms, which should give you 5 amps. So that's IRMS. Okay, so to find the peak current, remember IRMS equals I peak over square root 2. So to find the I peak, you just multiply 5 times square root 2, which should give you 7.1 amps. And it makes sense that the peak is greater than the IRMS because like the peak has to be higher than the root mean squared.
For that one, you could just use the V for IR. Right?
Let me think. Yes, you could. Yeah, good. Yeah, if you wanted to do it that way, you could, because you have V and you have R. So yeah, you could do it that way also. I just, for some reason, did it complicated. Okay, so number 25 is really similar to that other question that we had of like finding the electric and magnetic fields using the intensity one. So for now, I'm just going to skip this so we can get to some of the other questions, because this is basically the same thing, except they give you the intensity, so it's even less work for you. But I'll post the answers to this so you guys can verify that you understand it. But if you understood the other one, you should be good for this one. So we're going to try to move on. So number 26, this one is interesting. So it's talking about transformers. So as you guys remember, like the transformer equations, I2 equals N1 over N2 I1, and V2 equals N2 over N1 V1. And you know, like a step-up transformer, the voltage increases and the current decreases, so I can write that like step up, voltage, current, and then, up, step down, voltage goes down and current goes up. So this question's a little different than what you guys have probably seen, so I'm going to kind of explain something. So because of like the law of conservation of energy, whenever you have a transformer, each coil is going to get the same amount of power. So it says the secondary coil is connected to a lamp that dissipates this much power. That's going to be the same amount of power that'll be in that other one, and that's kind of why, because P equals IV, and if you have the same power, it's like this is constant. This is a bit of a side note, but that's kind of why when voltage goes up, current goes down, and why when current goes up, voltage goes down, if you guys were ever wondering like why that is. So for this one, so I said how the power will be the same. The power will be equal in both coils. So we can just say P equals IRMS times VRMS, because like this is VRMS, right? And we want to know the RMS current, and we're given P. So even though it's talking about the primary coil, we can still use the same P because it's the same. It is the same power. So it's going to be IRMS equals P over VRMS equals 80 watts over, and then you just use these same voltage, the same voltage right here, over 120 volts equals 0.67 amps. So you could be asked a question like this. I know this is a lot different than what you guys have seen, but yeah. So just keep in mind these equations here for transformers, and then remember this, and the power stays constant. Okay. So for number 27, it says a series RLC, so that means like resistor, inductor, capacitor, yeah, circuit. It has a 400 kilohertz resonance frequency, and you're given the formula for that. It's F0 equals, and that means resonance frequency. So that's going to be 1 over 2 pi square root of LC. So this one's a little weird. So the capacitor value is doubled. So this is the capacitor value, C, capacitor value. And then this is the inductor value. So we'll just kind of plug that in. And you can do this like with any equation when they ask you to manipulate things. The easiest thing to do is just kind of plug it in and see what happens. So if you have like 1/2 L times 2C, this is kind of an easier question just because if you notice these just kind of cancel out, right? Because like 1/2 and 2. So you still have this same thing, like it didn't really change, right? Because like when the capacitor value was doubled and the inductor value was halved, then it's going to remain the same. So it should just be 400 kilohertz still. But yeah, like if you had different values, then it would be a little different. Like you'd have to think about how it's on the bottom on the square root here. So you'd have to go about that a little differently. But yeah, so that's how you would do this question. Let's see how much. Yeah, okay. So for number 28, this is another single slit question. I don't think I put any double slit ones. I probably should have. So it says a 0.5 millimeter wide slit is illuminated by a light with a wavelength of 550 nanometers. So let's draw that. So this is 0.5 millimeters. That's very small. And this is the wavelength. This is how it's drawn in your book. This is 550 nanometers. And then over here, we're not going to worry about like the other fringes right now. We're just going to talk about the central maximum. Like the central maximum is like that one big space that you have, like the big bright spot that you have for single slit questions like this. So that would be W right here, and then this is the length. So it wants to know what is the central maximum. So W equals question mark. So we know that L is 2 meters, and then this should be A in the equation. I'll write the equation 1 second. This is A, because that's the width between, that's the width of the slit, I mean. So if it's 0.5 millimeters, it's going to be 0.5 times 10 to the negative third meters, which is, once again, very small. Okay, so we should be okay. So the equation, and this is given in your formula paper. So it's going to be W equals 2 lambda L over A, because we want to know what W is. So, and then I already said lambda equals that. So it's going to be 2 times 500 times 10 to the negative 9th times L, which is 2 meters. And then A is 0.5 times 10 to the negative third meters. I'm sorry? Oh, sorry. Hopefully I did. Yeah, 5. Yes, my bad. 550. I don't know why I wrote 500. Okay, so that's 550. Thank you. So you will get 0.0044 meters, and I did do it right in here, luckily. So 0.0044 meters. So that's how big the central maximum, like this right here, that's how big that bright fringe will be. Okay. So number 29, this is a refraction question. So it says a diamond is underwater, a light ray enters one face of the diamond, and then travels at an angle of 40 degrees with respect to the normal. What was the ray's angle of incidence in the diamond? So we're basically going from the diamond to the water. So I'm just going to draw it like this. I spelled diamond wrong. Diamond. So that's going to be N1 equals diamond, N2 equals water. Okay, and someone in like one of the other review sessions I remember asked me like, how do you know where the normal is? So the normal's never going to be like this line in between the surfaces. It's always going to be the line like kind of cutting the surfaces in half. So like that's how you know, like, so this is the normal line. Okay, so I know it doesn't give you the values for N1 and N2, but if this were a question on your exam, it'd be given to you. So N1 for diamond is going to be 2.42, and then for water, it's going to be 1.33. Okay, so we have that it's like going inwards like this, And we want to know what this angle is, right? Because it says what is the rays angle, what is the angle of incidence. Okay, so since this N1 is bigger, you know that this angle is going to be smaller than like this angle, so it's kind of going to go like this, and that's going to be 40 degrees. So you know that this angle is going to be smaller than 40 degrees because when the index of refraction is larger, then the angle that it makes against the normal is going to be smaller. And keep in mind, these are the angles that we're talking about. Like if they ever give you a diagram and it's the angle that's like against the surfaces themselves, do not use that angle. Like if it's like, let's say they give you like this one, then just do like 90 minus this one. But like that's not what you want to use for this type of question. Okay, so we'll call this theta 1, this is theta 2. So we know the equation, Snell's law. It's going to be N1 sine theta 1 equals N2 sine theta 2. So we're going to isolate, first we'll isolate sine theta 1. This is easier to picture. So sine theta 1 equals N2 sine theta 2 over N1. So to isolate, like you just want to know theta, so you have to take the inverse sine of this. So it's going to be theta 1 equals inverse sine of N2. It's going to be the inverse sine of this entire thing. So N2 sine theta 2 over N1. So that's going to be equal to inverse sine of 1.33 sine. So like remember we said N2 is the water, right? So 1.33 sine, and then theta 2 is 40. Always remember to make sure your calculator is in degrees if they give you degrees also. So sine 40 over 2.42, that's N1. And it doesn't really technically matter which one you make N1 and N2, but it just makes sense like for this one on top to be N1 and then like, so for the angle of like incidence to be theta 1, N1, and then as you keep going down, that's N2 theta 2. So if you plug this in, you should get 20.7 degrees for that one. And notice how it is smaller, so 20.2 degrees than this one. And it should be because like it's a much larger index of refraction. Like that's like a huge index of refraction. Any questions about this one? Should pretty much got it. Could you repeat that? I'm sorry. You can kind of think of it like, yeah, like to the normal, yes. Yeah, because like you can call it y, but like they could draw it differently. Like if they drew the surfaces like this, like if they said like that was the diamond and that was the water, then the normal line would be like this. So like, yeah, so think of it as the normal, not like the y, because that might confuse you. But yeah, that's definitely a good point though. So like that would be the normal. I know I drew that kind of weird, but like yeah, so like you look at the line against the angle against the normal. How long is this question? Okay. We're going to take like 2 minutes to finish this question because we need to do the survey. So, okay, so just very quickly, we'll go through this one. Okay, so this current is going to the right. Therefore, if you do the right-hand rule, the current's going this way. The magnetic field is going to be going out and then in, out. So these are all out magnetic fields, and this is in. Okay, so we're moving the loop towards here. Therefore, as you keep moving this loop in, you're going to have more and more of the outward field. So the magnetic field, B is increasing out. My handwriting's really bad now. So the induced, in this case, the induced would be in because it's increasing out. You have more and more going out, so the induced would have to be in. So B induced is in. So if you put your thumb in, and then if you kind of loop your fingers around, you should find that the current is going clockwise, right? Clockwise, yes. So it's just going to be clockwise like that. So clockwise. Okay. Okay, so since we only have 5 questions left, I'm not going to get to this one, but I will post the answers to this one on my WordPress site as well as the Study Union WordPress site. So we'll go ahead and finish right now. Thank you guys for coming. And if you have the survey, you can go ahead and fill that out. Put 80 in.